Good day, everybody. I'm Matej Hrušovský of Red Hat Research, and I'd like to welcome you to today's Red Hat's Research Days, March 2022. Firstly, let me introduce our speakers. The first one, Nikolaos Moraitis, Senior Software Engineer at Red Hat. And second, Gabriel Saz, a former Red Hatter and also a Ph.D. candidate at Masaryk University in Brno, Czech Republic, who will also be our conversation lead. And now I'll give the word to them to introduce our topic. Gentlemen, thank you for being here today with us, and the floor is yours.
Thanks a lot for the word. I would like to introduce the topic since it's also partly a topic of my PhD thesis. And at the very beginning, I will just lead you through some basic theoretical baselines from where you can really understand what we are doing, why we are doing, and why we are using OpenShift and some kind of high-performance computing to achieve this goal. And then Nikolaos will drive you through technical details of the solution. So I would like to start with scientific introduction into the project. First, I would like to mention the scientific method we are going to talk about. It's called quantitative spectroscopy, which is basically comparing observed spectrum of a star with a synthetic spectrum, the one that is calculated by a computer according to the known physics and theories which has to be involved in the process. So the next thing is important to mention that this quantitative spectroscopy is extremely demanding for computing time. So practical solution is to pre-calculate synthetic spectra and the model atmospheres for individual sets of parameter space. And then we use this data to calculate exact parameters for individual stars by interpolation. It saves a lot of computing time. So there's a generic method that's being used in astrophysics for 50 plus years. And we are going to extend this method. We are building on top of this method. So next, we would like to introduce something similar for rotating stars. And although you might say, okay, it doesn't necessarily need to be that complicated, but in fact, doing the same thing for rotating stars introduces 10 times higher complexity into the problem. And to demonstrate why it's so complicated, I would like to show you two images, which are showing us how surface of two quite known stars, one is Vega and the other one is Altair, really looks like from close by. You can see the temperature of the surface is not homogeneous. There is some kind of inhomogeneity on the pole. And the problem with this is we don't know actual inclination axis in advance. So if you want to calculate a synthetic spectrum of this star, you need to calculate it for each individual surface point to construct images like this. And the density of the surface point should be roughly about 10,000 surface points to get enough resolution to cover all the spectral features that we need to investigate this behavior. So next, you might think that 10 times higher complexity is not that high. The problem is that, as I mentioned already, the actual inclination angle is not known for most single stars. So to cover the parameter space, we need to also cover the parameter space in inclination angle and also in various equatorial velocities of the star as it rotates, because this gradient you saw on the images before, depends on the equatorial velocity. Is one of the very key parameters that we also do not know, and it's very hard to infer it from actual data we are receiving from the stars. So if we want to really cover the space, we need to construct a grid that will be extended by two other quantities. Next, we realized that if we calculate this on the desktop computer or on laptop, it might take like 100,000 years to calculate all the points of the grid. That's the reason why we need to optimize all the methods and run it on state-of-the-art hardware in parallel manner. That's the reason why we were searching for a way how to do it in convenient fashion. So we, next. Just to let you realize how complex this task is, each individual point of this plot, which represents originally planned web user interface for our project, which unfortunately had to be declined because we lost our web UI designer from the team, who joined other team and didn't have time anymore for further development. Nevertheless, I use this mock-up picture to demonstrate the goal. We want to cover as many points of the parameter space as possible. And you have to realize each point represents not a single point on the surface space, but each individual stars. So you need 10,000 calculations to calculate a single point of this plot. And this introduces only 2 parameters of the full parameter set. There's also a reason why we wanted to introduce these tabs on the top to explore all dimensions of the parameter space. So that's the reason why this task is so complex and why it takes so long and why it needs to be optimized. It's a kind of ultimate challenge for high-performance computing. We tried to do it in a cloud, but ultimately, it failed on many blockers. So we decided to go for our own dedicated hardware we have full control over. And we didn't realize that it's going to be maybe even more complex than our original effort. So as I'm going to show you on the next slide. The construction of our own rack was originally planned as an easy task. Luckily, Red Hat was able to donate all the funds we needed to buy required hardware that was ordered by design for this task. We planned which parameters we really need, and we ordered dedicated hardware to calculate everything for us. And unfortunately, things take long time because usually in academia, by administrative points, things are getting more complicated than in corporate environment. So since May 2021, it took up to September 2021 when we finally assembled all the nodes and found the proper place where to put the rack. I have to also say that most staff and the university tried to be really helpful. Even though it was in the middle of pandemic, we were able to fulfill all the tasks properly. We just had to wait for all the approvals, for a long time. In September 2021, we also realized that the public IP allocation doesn't work for our services. And unfortunately, we couldn't resolve it by ourselves. But we realized we are actually using a Red Hat product. So we contacted Red Hat support And by help of Reddit support, we were able to figure this out within a couple of weeks. And now everything works properly. So I just want to emphasize that the support of the Red Hat product that is being used in academic environment is still really valuable. And for people from academia, is a signal that they can still find value in paying the subscription for Red Hat products if they want to use them as a platform. So just to illustrate the complexity of the rack we installed, and in phase one, we installed the hardware that was bought from the funds donated by Red Hat. And this is the state from the September 2021. And this is still the base hardware we are going to use for the calculation. Nevertheless, we luckily got more hardware, which we placed just recently. Please show me the phase two, which is inactive right now because the Faculty of Informatics didn't provide us by the new switch yet, although it's already arranged and it should be installed by the next week. So we are extending our node structure by additional 18 nodes, which should increase the computing power extensively. And also this will allow us to share the cluster with the other departments and other research teams at the university. That was also tried a couple months ago and was successfully managed. And we are planning to extend our pipeline to be more universal and to serve also for the other scientific research projects at the university. Next, I would like to thank to our team, also to the team members who are not here right now, I mean, as speakers, but you can see them in the audience. And if you ask some questions, I mean, they can answer your questions as well. And now I would like to pass my word to Nicholas, who will tell you more about technical details of the solution.
Thanks, Gabriel. So, hello all. My name is Nicholas Moraitis, as been introduced by Batay as well. Thanks all for coming out, and just to continue about Gabriel's speech, and also try to explain exactly what was the pipeline of the calculation that we need, which is like more technical. First of all, I would like to point out that in order to calculate some of the parts in the of the results that we need, we basically use two main programs. The first one is the Atlas 12, and the second one is the SIGSPEC 49. Atlas 12 program is written like 40 years ago by a military program from the American military, and was written in Ada language. It's pretty old. The code inside is pretty messed up, and so we have to compromise ourselves in an unknown paths in order how to use it and try to figure out how to use the parts that we need from Atlas. And all these investigations was done by Philip Kubik, who is not representing today, but he's a part of our team as well. So in SIGSPEC is another program written in Fortran. Still has many problems since it was written by scientists and non-programmers. So we have to also compromise ourselves in this kind of unknown paths as well. So what is the pipeline? So the pipeline is that we need first to create a calculation. And as Gabriel mentioned before, for a single point of the grid, we need like 10,000 calculations. And we will end up having billions of calculations in the end, right? So how a single calculation looks like. So we create the calculation object, which we're giving it some input parameters. Currently, we're playing with gravity and temperature and other input parameters that are needed for Atlas 12 to calculate the first steps. And we split the calculation in 3 phases, in 3 steps. The first steps is Atlas 12S, which is like a parameter that is preparing the environment to run the actual calculation. And the second step will actually will spend more time in the calculation processing. So it will generate basically a stellar atmosphere model, which is written here, which is technically the model is a table of physical quantities that characterize one-dimensional stellar atmosphere in a function of radius, sort of. So, and yes, it's more complicated than it sounds. So, the third step is the synspec. We'll try to get that result as an input in order to create a synthetic spectrum, which is the intensity as a function of wavelength. And you can see here an example of the image that can be generated by those results, which is like two-dimensional. And in our case, if we have some OpenShift guys here, technically the calculation is like a custom resource that is using in our OpenShift cluster. And it sort of looks like this. And there is like separate fields here that all of the operators will use in order to try to complete all the pipeline. And I'm going to explain some of these parts in the next slide, which is we needed to find a solution in order to succeed the pipeline. So our solution was something like this. So this is like a product that we are writing right now, which is like in written in microservices architecture as it can be written in OpenShift, and we are trying to use all the Kubernetes and OpenShift related benefits that we can manage, right? There are few components here: the dispatcher, janitor, the API, the result collector, and the Vega worker nodes, which are like really important. And balance calculations are like technically custom resources that are being generated in the OpenShift cluster. So I'm going to explain this one by one, try to make this understandable. So the dispatcher, what it does is, dispatcher is the most valuable component in the whole product, actually, because it manages the calculation bulks and creates the calculations and distribute the calculations to workers, technically. So in few words, the dispatcher gets as an input a calculation bulk object. The calculation bulk object has a list of the calculations, including all the parameters that we need to calculate, right? So it reads that resource, and then it tries to communicate with a worker pools resource and see if we have any workers that are registered in that pool. And if there is like an available worker, then the dispatcher will create a calculation and assign that calculation to that worker. So the pipeline goes like this, and technically the worker will see that there is a calculation for his name, and start calculating. Then we'll update the worker pool that he's currently processing a calculation, and this is how all the components are communicated to each other, right? So if anyone is familiar with the microservices architecture, the most like known design is that for the microservices to communicate via REST API in a different way, but in Kubernetes and OpenShift we do things differently, right? And this is why OpenShift is really valuable for us right now. And the Vega workers actually is actually a daemon set that spawns pods for each node, right? So we join resources in our cluster nodes, and we label them with a specific label, and the daemon set knows that this is a node that is going to be used to calculate stuff. And this is important because Atlas 12 is going to consume most of the CPU, and we don't need anything else to run there, other than the other components that OpenShift runs on that node, of course, to manage it. And so this is what the worker does. It communicates with a worker pool, and it controls its state inside the worker pool. And one thing to mention also is that every pod is being registered based on the node name, right? So if we lose a pod and we have like another pod spawn up, it's going to register in the same place. So the worker is waiting for the calculation, basically, right? So it will get the calculation, and it will read the steps, and it will start executing the steps in serial, right? So this is important because we have a specific pipeline, and there are some special things that the worker does because we are special in a way, because the pipeline needs some specific input files, right? So those input files, which is that we have split it in control files and data files, are necessary for Atlas 12 to run, right? And there are some other input files that we need to generate based on our input data from the calculation. Once the worker finishes with the calculation, it's processing all the output files in the result storage. So currently, we are using the result storage as an NFS server that all Vega workers have that storage mounted. And this is the main storage that we keep our results as well. And once the calculation is finished, then the workers will change their state in the worker pool, and they say that, hey guys, I'm free now, give me another calculation. So the dispatcher will see that from the worker pool and grab another calculation or create another calculation based on the bulk that we have, and it will assign it to it, right? Also, one thing to mention here is that why we are using bulks and calculations. Basically, the bulk is like all the information in one place. And this is important because the scientist, and in our case, Gabriel, in order to figure out exactly all the parameters that we need to calculate, actually, we need to run a specific algorithm or some math, right? I'm not aware about this process, but this is really convenient for them because they can just write a Python script or a different script that will actually generate their parameters, and they can store it, generate a specific JSON output. Then our CLI can just read that output and create the bulk. And this is how we resolve this issue that we have. All right, so in order to somehow give interaction with the user, because we are not expecting for the scientists to have a deep knowledge of OpenShift as well, and in order to serve and expose our data in the Vega dashboard and the CLI, and have everything centralized, and for our UI as well. So that's why we have like our API, and the API just serves the creation of a bulk as a service, which like as I mentioned before, you can get the bulk file, which is like generated by the scientist script, and create the bulk, right? And also the Vega API is responsible for exposing all the information about all the objects related to the pipeline. And I'm speaking of bulks, calculation, worker pools, and even you can use our Vega API to download your results, right? So the Vega dashboard is uh, an UI that scientists can just go and do things with a user interface, which is like convenient for them as well. And another component is the result collector. So what this component is important because we don't want to spend time for the worker to try to organize the results in the storage once it's finished, because if you think about it, if we add another minute in the while processing a calculation, so if you multiply that minute with some billions, this is like a lot of time, right? So and also we don't need to do that in serial, and we can do that like in parallel. That's why we have another component named result collector, which what it does is watches calculations. If the calculation is completed, then it goes to the result storage and deletes actually all, some of the debugging files that the Atlas 12 and CSPEC are generating in order to save storage as well, because we need petabytes in the end. And it stores them in a specific folder that we keep all our results. So in the future, once we are going to go to production and our cluster is going to run calculations every day, we are hoping in the end to have a very big database of calculations of the results for every different combination of parameters, right? So in the future, if another scientist needs to calculate some combination of parameters, we could have some of the calculations already calculated, right? And also the name of the calculation is also generated by the input data, which and we create a hash code from it. So somehow we know exactly that we have already calculated that calculation, and we can just give it to the user, and in this case, the scientist. Janitor, it's I think that this is like a pretty clear name. This is like responsible for garbage collection for all the processed calculations. We have a specific retention time. I think that this is pretty common in microservice architecture designed program, which is when we create so many calculations, and we are talking about billions of calculations in total, and we don't know how OpenShift will behave with billions of data on it, right? So I don't think that this is like advisable. And also those calculations are basically useless after they have completed, right? Because we have all the results there, and the calculation bulk can hold that the specific calculation is completed, and we can use it like in a history. And last, the CLI, which is like a Golang program named CCBOC that you can find also in our organization, which basically we are trying to create a CLI to make the life of the scientist easier, right? So you can create the bulk directly and get off some of the details. I'm going to show some of the stuff in a demo next, and pretty much this is the non-detailed, I can say, design of the product, because there are a lot of things coming with any other component, because we're using specific controllers. For example, the dispatcher here runs 5 different controllers that we're watching the cluster and so on. And one thing to mention here is that since we are in OpenShift and in the Kubernetes environment in general, right? So we can have like Prometheus metrics and Grafana dashboards and alerts using the alert manager, of course, in order to monitoring everything, because once we will start calculating, maybe this process will take 1-2 years, depending on the amount of workers that we have right now. And this is really good for our team as well, because if we are failing to calculate a specific combination of parameters, then we have to debug it, of course, and we have to collaborate with some of the scientists to figure out what's happening. And there are also some other technical obstacles that we have, because we are using Atlas 12 and Synspec 49, and we had like many bugs with those two binaries, and because they were written like in a different way of thinking 30 years ago, the programs were have different thinking. Like for example, in some point we had a calculation failing, and once we were passing the temperature up to 10,000 Kelvin. And the problem in the end was that because 10,000 Kelvin is 5 digits and no 4 digits like 9,000, and that was creating an extra empty space in the input file, and the whole calculation was failing because of that, and we didn't have any debugging error. So just imagine ourselves debugging the hell out of it. So it was really bad. But either way, so I would also like to share with you some of the process that we're using. On the left title, you can see the worker pool. So I'm just watching the worker pool. You can see that we have some of the workers there already registered based on their node name, as I said. In the middle title, I'm just watching for the calculations. Right now, there is no calculation created right now. And from there, and in the left side, I'm going to type some commands in order to calculate, to show you guys how we are doing the process. And this is like a pretty trivial demo, so it's going to bear with me. So this is an example of the file that the scientist can pass as an input, right? You can see here that there are two main fields, which is like the worker pool, which is which worker pool is going to be used to calculate that bulk. Well, in our infrastructure, we don't need many worker pools, of course, but we can split the workload in different pools. And the other one is a calculation, which is like a mapped table of calculation based on their name. And this is like an example, and I'm using like two parameters here, which is like the gravity and the temperature. This is going to be more complicated, of course, as an output that the scientist is going to generate. And the steps are the 3 steps that I described in the calculation pipeline, which is like Atlas 12, has Atlas 12R, and Synspec 49. So using that file, you can just create the bulk using our CLI. And as you can see here, that once we created the bulk, immediately the dispatcher so that it got in an email actually from the controller that a new bulk was created. So what it did is like it took like every calculation and create the calculation and assign it to some of the workers. If you can see here, some of the workers here change their status in the processing. So this is the start of the calculation, definitely. And of course, in our example, we have less calculations than the workers, but In case that the calculations are more than the workers, which is like the normal case, the dispatcher is only going to create calculation based on available workers and not more. Once a worker is available again, then the dispatcher will actually create a new calculation. So this is a part that using our CLI, CCBOC, you can just get some information about the bulk, and this is like in which phase is the calculation. Of course, this is like not like visual very good because that's just a CLI. This is why we are planning to build our UI as well. And of course, if anyone from the audience is like a front-end developer and he can help with us with that, we are really glad to much appreciated. And so the calculation object is, as I saw also in the pipeline, is just like this. And you can see here that we have the phase which is processing. There is a few labels here that other controllers are using to communicate with other components. And one of the important fields here is the assign field, which is in which worker this calculation is assigned. And every step, you can see here that the first step is completed, and the second step is currently running. And pretty much once this calculation is completed, then the calculation is marked as done. Then the result collector organize the result data to the NFS storage, and then the user can just use the CLI to download the data, or the UI, of course. And pretty much that was it. And so if anyone has any questions, and also I would like to thank everyone that are attending the presentation.
So during the talk, there popped up 8 questions together and in the chat. So I think before addressing another questions of the audience, maybe we should address these 8 questions. What do you think, Nikos?
Yeah.
Yeah, the first question is about James Webb Space Telescope, whether it does run on Linux. And I have to answer this one. Unfortunately, James Webb Telescope uses Siemens as a software contractor, and Siemens was developing the dedicated software solution for the mission. So it's closed source, and it's something that was developed to minimize energy consumption of the telescope. So that's the reason why they opted for the dedicated solution on top of reusing some software that's already available.
Yeah, also it's worth mentioning also, I replied us in the chat, but I can rephrase it here, that currently we are collaborating with a team from the European Space Agency that are trying to run some calculations in order to set a new telescope, X-ray telescope into space in the next months. And they are doing that using our infrastructure and OpenShift in general. So this is like a big win for OpenShift, I can say. And also this inspired us actually to refactor our product in order to accept new different calc pipelines. And this is really difficult because every calculation pipeline has its own special things. For example, we are of a need of a specific input files, and we need to do some symboling linking inside the NFS storage in order to make all of the files accessible for all the calculations. This is like pretty specific for our pipeline, but not for them, right? So this inspired us to work on getting our product ready to be used for different kind of calculation pipelines.
There is another question popped up just right now by Eduardo. I'm not sure whether I understand the context of the question, whether it's related to JWST or it's related to our infrastructure. So while I'm waiting for him to, for Vega itself, I will ask Nikos.
I just wanted to point out, if he wants to join with audio and video to clarify his question, he can. So we don't have to have people ask in chat and then have you try to interpret. He can just join directly. So if you look for the button that says share audio video, you can ask yourself.
Yeah, that's equivalent of just get the microphone, that's the question, right? So I think that is the best if Eduardo wants to do it. Otherwise, we can just answer the question here.
Yeah, I mean, so Eduardo already mentioned that it's why we do not use Tecton plus Argo CD architecture for Vega. I will pass this to Nikos.
Yeah, because as I mentioned before, is what we are trying to do is not yet done before, and we need a specific pipeline in all the components, how to manage all the calculation pipeline, right, and the results. And in general, that we had to write something from scratch about it. And there are a lot of technical difficulties, and how Atlas 12 and CSPEC 49 are behaving, and how we want to use our nodes in order to calculate the data. And there are many, many other things to consider. And instead of just trying to figure out how to do it with third-party tools, and we thought that it's better to start writing our own. And also in the middle of writing, it was that we were discovering some things that we need to resolve or some things that we need to change. So and because we were writing our own product, we were really flexible in order to achieve that.
I will just add to the Nikolaos's comment about another team using the infrastructure. What we are simulating, or they are simulating on our infrastructure, is actually a simulation of magnetic deflector, which is protecting the sensor from particles coming from solar wind, because X-ray telescopes are usually affected by these high-energy particles, and these particles are introducing a noise to actual astrophysical data. And this deflection that was never used on the space mission like this before was simulated on our cluster. And if there are no other comments or questions to this, let's move on to the next question. Chris is asking whether the calculation take 1 or 2 years. Yes, I mean, if you want to cover a complete grid, it takes about 1 or 2 years. So nevertheless, even partially covered grid is already a success. So we will just recover it eventually.
So there is another question in the Q&A. I think we can address that as well.
Yeah, I mean, I think we will go through the questions we already have in the buffer, and then we will go to the Q&A question. I mean, I will just add it to the buffer. So let's move on to the next one. That's going to be very interesting, and I'll also pass this to Nikos, and that's public IP issue. I mean, so one of the participants would like to appreciate the details about it.
That was a funny story, actually, because the infrastructure is hosting a private network in Masaryk University, right? This is pretty common, like having a bare metal OpenShift cluster running on a private network. I guess we have some customers that have this kind of infrastructure. The problem was that we wanted to expose our some of our services, of course, and the problem was that the networking team in the Masaryk University didn't want to use some NAT forwarding to the private VIP that we are using for the router, and because of and we had to do it with static routes, right? So that was creating some kind of networking loop because OpenShift was rejecting that. So we have to figure out how to do it, right? In the end, we had two problems. The one problem was that to expose the router, which is include all the applications around to OpenShift, and the second problem is to expose our API, OpenShift API, not Vega API, in order to make our OC command available, like without joining any VPN. And the problem was in the two phases. We figured out how to hack actually the route service in order to add the external IP and also to change the OpenShift configuration in order to accept this kind of public networking. That was done after opening some tickets in the support, support, and all the guys were really helpful. And we spent some days in order to figure out, to explain actually our problem and what we need to do. We, in the end, we hacked the service and we did this workaround. And the only problem was left, it was the API server. And in the end, we'll have to deploy our own load balancer in a different server. So right now, because OpenShift can manage that, OpenShift load balancer in default. So this is possible in OpenShift. So if you have like a really complicated networking, OpenShift can just allow you to have your own load balancer, which is like really normal. We didn't know that. We were hoping for to have something ready. But after another support ticket and some other days of debugging, investigating, we figured out how to resolve the issue. And if anyone from the support team is here now, and if he sees the recording right now, I want to say thank you for the help.
Okay, so let's jump into the next question. Hopefully it was understandable. And next question is related to why we didn't use F2C to compile the Fortran code into C. And I would rather answer this with a very simple thing. The code is quite sensitive to the version of the Fortran compiler. It can be compiled with any Fortran compiler. And therefore, using F2C would introduce too much overhead for debugging why it doesn't work in F2C. And it's very likely that even resulting C code wouldn't work properly because the code is written in a very, let's say, inconvenient way, and it's not ready to be transferred to the other programming language. So we just stuck with the code as it was and compiled it with the recommended compiler by the author. Next question is from Carlos Camacho. Do you have by any chance information about the dispatcher? Is it open source? Is there a public repo for reviewing? Though it was already answered in the chat, I mean, I would pass this to Nikos so everybody can hear it.
Yeah, what we're building now is open source. You can see also our organization. Everybody can collaborate there, and any contribution is welcome. And we also plan to keep it open source, of course, because what we are doing. Just to mention that our project is something that we spend our free time, and this is something that we want to contribute to the scientific community. And of course, what we're building is open source. And any request for extending the product is appreciated. Any contribution is appreciated. So, yeah.
Yeah. Thank you, Nikos. Hopefully everybody got it. I mean, this is going to be open source. It was decided to be under GNU GPL license, so it could be used by any other project in the future that we can build on top of it. There is another interesting question from one of the participants. whether we can say something about at least an order of magnitude, about the size of the input data sets or output data sets, whether we have to dispatch both code and the data, or the data can be shared or something. I would pass this to Nikos. I mean,
yeah, I will need some more codings about the question.
Yeah, I think the participants meant whether we will need to process the data for each individual calculation separately, or the data can be shared among calculations. And what's the size of this data, the size of input data, and the size of the data that is going to be written in the output?
Yeah, technically it's how we are constructing a calculation. We are now based on specific parameters, right? So there is no like point to share the same a specific parameter that's like the same in different calculations, because the amount of data is really trivial. And so if someone wants to calculate something that we already calculated, we're able to detect that and just give him the results directly. And this is like a dream for us, that in the next years we could have like a big database of data set with already pre-calculated data, so the scientists can just directly use them to run their own combination of parameters in our calculations. Is that answering your question? I think.
Yeah, it seems it answers this question. So let's move on to the next question. Nikos mentioned that we could rerun a calculation on a daily basis, and he would like to ask whether there is any deadline for a schedule, or we can finish the calculation anytime we like, or there is some other project that's depending on the schedule. I can say the only deadline that is given by this project is regarding my PhD thesis. So I would like to have the results as soon as possible. I mean, because I would like to finish my PhD with 10 this year, or maybe next one. And that's the only limitation. Everything can be run asynchronously. There is no other experiment is waiting for the results. Yeah, there is another participant asking what's the data size per computation. Probably that's important to know how much storage space we need. So Nikos, can you answer this?
Yeah, so just imagine that every calculation, the results, if we trim all the unnecessary data that are generated by the calculation, it can be a few megabytes, but the calculations can be like billions. So in sort of, we can reach like hundreds of terabytes. And right now we have a lot of storage, and I don't think that we'll have a problem in the future with storing all these results. But the ideal scenario would be to have a centralized data center with all the results, so every scientist all over the world can just grab them. And in the future, we will need to have our own website serving this purpose.
Yeah, just to remind you, I mean, I had it on my slide, but we have 12 tera drives, which we have 8 PCs and currently running on RAID 6. So that should be far enough space to store all our data. Next question is also for Nikos, because one participant is asking, how are we queuing our jobs and batch scheduling of the jobs.
Yeah, actually, that was another reason why we wanted to create our own product, right? Because if you want to create a job in OpenShift, right, what you are doing, you are just like creating new pod and run it, stop the pod, right? So if you add the amount of time that you need to spawn a new pod every time, we just added like few more years in the whole process. So and also we thought that the worker pod that we are using right now, it just run there, never stops. It calculates the one calculation and then continue to another one. So the pod itself it doesn't need to respawn. And so how we queue them is based the responsibility from the dispatcher component. So the dispatcher can have like based on the time of the calculation bulk host created, he just grab calculation and spawn it. And once a worker is available, then a new calculation will be created, and the worker will just immediately start executing the commands in the same pod and generate the output data in a different folder in RFS server, and the results organized by another component. And in the end we gain like some years of running calculations by not spawning new pods and not queuing different jobs, right? Does this answer your question?
Yep, probably we can move on the next question. I think it's plenty information on queuing. There was some clarification regarding what was meant by the size of the data, and it turned out that we probably didn't answer this yet. And so I asked Nikos whether he can go to the slide with the pipeline schema. And because one of the participants, not this one, the previous one. Yep, exactly, this one. So, and the participants asking about the data size that is going to be shared between this Atlas 12S step and Atlas 12R step. So probably he is wondering what's the size of these files which are going to be passed to the next step.
Yeah, the size is like few megabytes.
Yeah.
But the calculations can be like billions. So
yeah,
megabyte is it's large enough. Right? So.
Yeah, so that's an important thing to be mentioned. I mean, these calculations are running it's a numerical solution of the differential equations, which is iterative. So it's running over and over again. So it's getting the result, and these results are going to be used as another input, and there are many iterations. So even though the input data size is pretty slow, I mean, the time required for the calculation is determined not by the size of the input data, but by number of iterations that are required for the model to converge. So that's a kind of different kind of data processing. And also the results of Atlas 12 that are going to be passed to SynSpec is just a text file that has a couple of megabytes. It's not a big data, but SynSpec again does some numerical integration of this file, and it solves differential equation for every single layer. It basically does ray tracing for every single frequency bin in order to calculate the spectrum, and depends on the frequency range of the spectrum that is being set by the parameters, and also the number of elements that are involved in the process. So that's these are factors which are not influenced by the size of the data which are used as input files. Also, the output, the final output is again just the text file that is only a couple of megabytes in size, but it can take like half an hour or even several hours to calculate it. So. So if there are no other comments to this question, let's move on to the likely last question of the buffer, and it's whether we can elaborate on the net scientific output of this project. What are we adding to the library of model synthetic spectra to account for rotation of the stars? For example, like whether we are also calculating a set of abundances, metallicities, and play with the rotational axis to generate spectra. How would such library of spectra be subsequently used? I love this question because it's really addressing the science of the project. And I'm really glad to answer this. So the scientific output is basically a grid of pre-calculated models for the stellar atmospheres. I mean, for those who do not know, stellar atmosphere is the only part of the star we can directly investigate. So this part of the star from where the light is coming from. So, so the spectrum is a kind of fingerprint of the stellar atmosphere, and it's telling us all about the physics that's happening there. And we can calculate spectrum for every single parameter set. What we can do, we can just select discrete parameter combinations and calculate spectrum for these parameter combinations, and then we can interpolate in between. And what we are doing in comparison to existing stellar atmosphere grids, we are adding two new dimensions, and that's equatorial velocity and inclination of the rotational axis. In the rotational axis, we are adding 10 more steps because we are doing inclinations only for every 10 degrees. I mean, this density of the coverage of this parameter. And for equatorial velocity, we are considering now a step about 50 kilometers per second. And there was already a proposal to cover even denser parameter space with this. So what can be possible outcome? We can calculate synthetic spectrum for a star that we know already there is possibly a fast rotator, but we have no idea about actual inclination of rotational axis. So we can use the model to calculate the inclination just by comparison of the synthetic spectrum and the actual measured spectrum. So that's something that was never done before, or actually it was done before, but for individual selected stars, like I already mentioned Vega or Altair, but there is no existing grid that allows you to do it for any data you will measure in the universe. So our goal, I mean, is to use the data from the space mission like Gaia to do this on a huge set of stars, to investigate the effect of rotation on structures like star clusters, for instance, or dwarf galaxies, how distorted are our data, our knowledge of these objects by neglecting the rotation, because rotation is mostly neglected because it's introducing a new level of complexity. So it's mostly uncovered completely and ignored. So we might redefine the whole stellar astrophysics, I mean, by introducing the easy way how to calculate the rotation. It's a kind of simple summary of the importance of what we are doing. I don't know whether you did answer this question. Okay, seems it answered the question properly. In the meantime, I mean, I see no new question. So if there is any further question, I mean, please ask, don't be shy. If you want to ask by microphone, just ask for the permission and you can jump in. We are happy to answer whatever question pops up.
Also, one thing to mention is that we appreciate any contribution, and if anyone that is listening wants to be a part of the project, and help us out with many issues that we have also as well, and also to speed up all the purpose of the project will be much appreciated.
Yeah, the project is basically aimed to calculate these things as soon as possible. Sooner we will have the grid, sooner it can provide a baseline for the next research that can be built on top of it. It can very likely convince people to do not neglect the rotation in their research when it comes to the stellar astrophysics, and it might change a whole field. Since I don't see any further questions, I mean the last call for questions. Seems there are no other questions. Nikos, do you have any closing remarks?
I'm trying to speak. Can you hear me?
Yeah, we can hear you.
Oh, okay. I'm trying to share my video. That's not working. Anyway, it doesn't matter. You can hear me, so that's great. It is fascinating. This is Nathan with Red Hat, and I'm in sales. I don't work with in as much detail as I saw here, but I'm fascinated by that. If I do understand the call for working and contribute to advance this project that is way past the design phase, understood. But if I were to bring forth this idea to customers in the field, who are the, I want to understand the profile of customers who are likely to be interested in the problem domain that this is addressing. Who would be interested in this type of work for them to engage directly as well?
I would like to answer, and then I will pass it to Nikos because he might have further comments. So what I see from my perspective as a academic worker, so this would be very interesting to all universities involved in the fundamental research projects and also some applied research projects, because this is introducing the way how OpenShift could be used as a platform for high-performance computing. So, so in an easy way, and also how it can be incorporated into the development of scientific projects, which involve some simulations and parallel computing. Because so far, scientists and academics in general are not using OpenShift for this. They are usually running it directly on top of hardware nodes. And the OpenShift is already providing many goodies which would simplify their job a lot. So, and this is a kind of pilot project which is has objective to demonstrate that OpenShift can be used in this way, because OpenShift is a tool that was primarily developed for the purpose of developing other projects. So it's basically a tool for developers, but not for scientists. And scientists are mostly unaware of this possibility. So that's my point of view. And maybe Nikos has further comments.
Before we go to Nicholas, Gabriel, I did want to follow on to what you just said. So I understand that. Now, corporate America does collaborate with academic institutions in research. There are companies who fund different types of projects, of course, to advance their own goals. It may be a pharmaceutical company, trying to piggyback or use the brain power available from academia to advance specific projects. So are there certain types of companies that are more likely to want to partner with academia on this type of scientific, in this field, Gabriel, before going back to Nicholas?
You mean the field that is particularly related to this research?
Yes.
Okay. In case of stellar atmospheres, probably the only interest of industry in this kind of research is related to the construction of space telescopes and in telescopes in general. So, I mean, this particular field is just creating opportunities and challenges to the engineering industry, which can be then recycled for the other applications. So that's the primary benefit of astrophysics as a field, because it's motivated just by pure curiosity, but the tools developed for this purpose, I mean, could be then reused in the other context. So this particular field is probably doesn't have any direct applications for the industry, but it can introduce a challenge that it could force industry to develop technologies that wouldn't be developed without this motivation. So that's my point of view on this. But this kind of project, after we will make it more universal, after the pipeline will be universal, could be used by any industry that needs high performance computing. Doesn't necessarily have to be fundamental research project. It can be calculation of whatever they will define to be calculated in parallel way on top of OpenShift platform.
Yeah, also, I just want to add that after we are going to be more universal, like, and we're not depend only on specific pipeline. And since that our product is open source, OpenShift is open source, we give an opportunity to startup companies to use it as to calculate their stuff, right? Also, other companies like CERN that are already using Kubernetes for different kind of approaches. And why we're using OpenShift can maintain the calculation pipeline for years, right? So if you can just like use a Kubernetes cluster to calculate something on the spot and you're done with it, but OpenShift has more abilities to maintain a production infrastructure, so the developers can directly go to continuous delivery of their product, or how they calculate the data and monitoring and all this stuff. So I'm hoping that our product can be used from CERN, NASA, and other space agencies that they're being used to calculate stuff like that. And if we exclude the fact that they have their own personal infrastructure and their own personal private programs that they're calculating some pipelines, right? But we step forward in the open source way, right? And by using OpenShift, we give also the ability to be used in a production environment, and also any company that can start up or corporation companies can just like use our product in the future. And this is how we aim.
That helped. Thank you, Nicholas.
I will add one more thing. I mean, we already mentioned that there was another project which were used, we were using our cluster for like 2 weeks, which was related to simulating deflector of the Athena mission, this upcoming X-ray space satellite, which is using the code that was developed by CERN, because the deflector works in exactly the same way as supercolliders in CERN. So they are just reusing the same code, which now they are running on top of OpenShift. It was never run on top of OpenShift before. So this is the first time of this application. So we can directly address this and tell CERN that, yeah, we have container that can run on OpenShift and it can run your code in a more convenient way as you are using it now. So basically, in case of CERN, we are already introducing the science case for CERN.
Sense.
Are there any other questions? Maciej is asking whether, or Maciej is passing the question by Jerzy Podiwin, whether there are any atmosphere models based on shaders or other methods that could leverage GPUs. Currently, I'm not aware of any, to be honest. I'm not aware of the models which are using GPUs, because the code that is being used for these calculations was created during the time when people used punch cards to distribute the code. So I don't really believe there is any optimized code for GPUs. Any other questions? Yeah, I will ask Nikos if he has any closing remarks to the topic, and then I will add mine, and we might close the discussion. If anybody, there is a funny comment, maybe we need a punch card reader for GPUs, then yeah, that would be nice.
Yeah. Yeah, from my part, I would like to thank everyone. It was a really nice experience, and thanks everyone for all the questions and all the energy that you shared here in the chat. And also, I would like to thank you and thank in overall the Red Hat Research Group and Hugh Brook, which make help our dream and make it possible for the funding and all the infrastructure that was acquired by our project. So a very big thank you to everybody.
And I would like to thank everybody, every organizer of this event, for giving us an opportunity to share with you our results and our progress. And again, thanks for all the support. So I think I will pass word to Maciej Hruszowski if he has any closing remarks.
You did.
Yeah, I forgot to click, sorry. So there's really not much to say, but to thank both of our presenters for a wonderful presentation. Thank you to everybody who asked some wonderful questions today. Thank you for being here, and we'll see you in a month.